Yeah, perfect.
Good, very good.
Sweet.
Super one today.
Yeah, so hi everybody. My name is Chris Fourie. I'm a PhD student at MIT with Professor Judy Shaw. And
Matt Boyd, I will also work in Feelings Lab as a research engineer.
yeah, so today we basically just wanted to, well, we wrote a position paper, right? Talking about the need to simplify open source real-time systems for human-robot interaction. Right? And it's interesting for us because we tend to think about this more about robots in industry and how the technology is evolving there, right? So it's really interesting because when you look at collaborative robots in industry, it sort of typically implies this idea of coexistence and not really collaboration as we tend to typically think about, right? And sort of a large part of the focus is in reducing costs, right? So you want to remove those cages, make robots safe to work with, right? And then you have less infrastructure costs when you integrate a robot into that setting, right? There's not really talking too much about augmenting workers in these production environments, right? But at the same time, like, you know, a couple of years back, we went and we did a series of surveys. We interviewed a bunch of robotics companies and we asked a lot of key players in the field, like manufacturers, you know, what kind of technologies are changing, how it's evolving, and, you know, what they see the growing need for, right? And when we spoke to them, one of the things that they kept talking about was this need for flexibility, right? And it's a pretty complex picture, right? When we talk about flexibility, because you can think about it in terms of like the structure of the company, but then also technology itself. But when we start thinking about HRI, right? When we start thinking about what HRI can do, HRI sort of plays this really interesting and compelling role, right? Where we start talking about partial automation, right? Where we can improve the productivity of a worker, right? But we can also improve, say, the economics or the quality as additional metrics that, you know, robotics can actually help solve, right? And this is getting more and more interesting in today's environment because there are very difficult challenges ahead, which everybody's looking at technology to try to solve, right? So in particular, so for example, in the US, right, there's sort of massive labor shortages that we're looking at with 700,000 plus, you know, open jobs that can't be filled, right? And then, of course, here in Europe, one of the things that constantly comes up is this idea of an aging workforce across industry, where your average, you know, manufacturing worker is over 40 years old, right? So it's a very different picture to how it was 20, 30 years ago. So all this being said, right, we have this like great business case, right? But we see very few implementations of actual collaboration in, you know, manufacturing settings. And the question then is, where are the robots? So if we take a step back from that and we start looking at, you know, the IFR, which is the International Federation of Robotics, and we look at how they are, you know, talking about all of this, they will talk about, you know, collaboration with industrial robots, and they'll highlight that there's basically two main types, right? So it's this idea of coexistence, and then this idea of like sequential collaboration, right? And then off there in the right-hand corner, the thing that we should be working towards, according to the IFR, is this idea of responsive collaboration. It's this idea of the robot being able to respond in real time to you, right? And in real time to the movement of the worker, right? And I guess fundamentally the question that Matt and I have been discussing and what we wrote this paper about was, you know, what makes this so hard, right? You know, why do we not see more of these systems? And we looked at it basically from the viewpoint of our own work, right? So when we start looking at real-time systems, you know, and the complexities around it, right? You know, the first thing that springs to mind is sort of, you know, why do we need these things, right? And real-time systems basically help us to maintain high levels of robustness and reliability. It's really critical for time-sensitive, you know, features such as safety. And then, of course, you know, if we start talking about responsive collaboration, there's not really a way to do that without real-time interaction, right? But there's a lot of really confounding factors, right? So we've got, you know, high setup and development costs. We have a lack of, you know, dedicated frameworks for real-time interactions. We also have a lack of definitions, which is making a lot of this very, very complex. And as a result, what we're seeing is sort of limited research and deployment of real-time systems in HRI. We're not really talking so much about, you know, robots responding in real time, right? And so Matt and I dug through, you know, a few of the conference papers, you know, from the last few years, and you know, typically we don't actually see, you know, much in this field, right, of these kinds of interactions, you know, this kind of modeling. So, yep.
All right, so that kind of prompts an interesting question of what is real-time, when we say a real-time system. Outside of HRI, there are standards, and we've spoken about standards a little bit today. I think Shelley is not here. we talked about some of the standards do exist, but they tend to be about very specific aspects of the system and not about the kind of system implementation. So it's things have to happen on X timeline or this kind of hardware, this software definition, and they tend to exist outside of HRI. And of course, within just computing in general, but also in HRI, our interpretation of what real-time means can vary by your field or the application. So in formal computing, which is a bit of my background and Chris's background, we think of it in terms of utility and utility degrading beyond a certain deadline. But that deadline can be nanoseconds to hours. The time is irrelevant. It's the deadline and utility related to that deadline. In human factors, we can speak of low latency, where it's a function of how the human interprets the interaction, which tends to be sub-second timing, but is also variable. Audio, obviously, we think of low latency in terms of jitter. Imaging, we think of throughput for image processing. We talk about frames per second. And of course, in AI and neural networks, we just really consider online versus offline, where online can mean practically anything, let's be honest. And so this brings up a challenge of juggling the different requirements of all of these different parts of the system to build safe, performant, and useful real-time systems that might need to incorporate all these different fields. And so where do we start? So at the base level, we've got existing kind of embedded or bare metal systems where we get hard real-time definitions. They're very difficult to implement, really limited functionality. Very few people work in this space because it's very low level and difficult, but it gives you hard real-time guarantees at kind of any time frame you wish. A step up from that, we've got dual kernel systems. Some people use these in HRI research and in robotics. They're good for giving you better performance guarantees. However, they're still very difficult to implement. Most people are probably familiar with the third bullet point here, the modified operating systems, preempt RT, or the real-time Linux. It's got another funny, silly name. But these are relatively easy to implement. They give you most of the functionality of Linux, most of the real-timing-ishness that you want. And then one step above that, of course, is the middleware, where most of our lives exist in the ROS or ROS2 world, where we can get varying levels of real-time compatibility. But again, it's easy to implement kind of out of the box, but difficult to maintain that performance, because as you add more packages, you add more nodes, you add more things you don't really understand underneath, you go from, oh, great, this runs at 100 hertz to all of a sudden it's running at half a hertz, and I don't understand why. I just added a whole bunch of packages. And so for me, the challenge here is balancing the performance of the system with all the added functionality that we wish to achieve. And of course, the technical knowledge requirements for all of these different levels of the system.
Yeah, so we actually ran into a lot of these problems, fairly recently. So in my PhD work, which I've been collaborating with Matt on, we've been looking at sort of dynamical systems-based collision avoidance, and particularly its application towards, more non-convex obstacles. And we came up with this really nice real-time method. So we had this ability to model a lot of complex things, like non-convex obstacles, point clouds, geometric obstacles that we can just directly integrate. And we're able to actually implement this on a Franka Emeka Panda robot, with the actual dynamical system running at 1,000 hertz, right? And what's really cool is that we're able to do that with 240,000 samples using a GPU accelerated, version, right? And that's to get a full result with the, end to end, right? With the GPU. So courtesy of Matt, actually. But yeah, the whole idea, right, is that we were working towards this safe and real-time navigation in a changing environment, right? And we have these implied utility problems, right? Where the position of the person's hand is going to make a big difference to the performance of the system. And when we start talking about safety, right, then we want a minimum latency system, right? So for example, one of the features here was that the robot can react in real time to obstacles in its path, right? So the robot will plan around you, right? But then also we want safety stops, right? So on the right-hand figure, we want the robot to stop, right, when we actually get too close to it. And it's interesting because when we start looking at more complex interactions with these things, right, what we actually start seeing a lot of the things that Matt was talking about, right, where the dynamic performance of the person is something that we want to explicitly be able to accommodate, right? which means we want our systems to be as fast as humanly possible. So, we spend a lot of time working this and making sure that it is minimum latency, and maximizing the bandwidth of our system, right? And we're able to actually use it to, work in real time, and have the system respond to a person, and we've got pretty good bandwidth and pretty good performance, and it ended up working pretty well. But what made this hard, right, was a couple of questions that we found really hard to answer. So, for example, there's this idea of like, how do we ensure a minimum latency system, right? When we know that the utility of position measurements sharply decays the longer we have to wait for them, right? How do we ensure a high bandwidth system, right? So we want to, capture that full range of like human motion, right? And, this sort of leads to this like shared memory, multi-threaded system design, and it's very difficult to actually balance, how do we balance threads and prioritize subsystems? It's difficult to do correctly, but it's even more difficult to be sure that we did it correctly, right? And that is an ongoing and an ongoing challenge, right? We want our systems to be better, but we aren't necessarily sure where we can improve it. So,
So I'm just going to talk through a little bit of kind of next steps of where we're headed with the system Chris just described. So it was designed with optical tracking for motion planning, as we frequently do in this space, OptiTrack, which is super fast and works well in this system where we want things to run at 1,000 hertz. However, it's fragile, you got to recalibrate it constantly, and it's super expensive. So you can't take this and move it into a factory, into a work cell, and put an OptiTrack in every single work cell. So it's expensive and cumbersome. So we prefer generally a generalized solution based on something like RGB cameras. They're inexpensive and pretty flexible, but they are relatively slow. 30 hertz on average, although some are faster, some are slower. By the time you add in the point cloud filtering to filter out the robot in the scene, now you're down to 20-ish hertz. And if you're going to add any AI on top of it to track the objects in the scene that the human is interacting with as well, then you're down to 10 hertz. And so you're stuck with 1,000 hertz planning system and control system interacting with this 10 hertz at best perception system. And so you've got a lot of challenges there in integrating those systems together. Not only coordinating the compute across different physical infrastructure, as Harold showed us in this picture, all of the computers you need to run these systems, but also then how do you gracefully degrade performance, and where do you make the choices where to degrade that performance as you're making these trade-offs between these two systems. And then, of course, one of the big challenges is system design, getting it all to work together. And so, we talked about close proximity interactions generally motivating real-time interactions, especially when you are very close and doing reactive and responsive interactions. And so there's a lot of systems that already exist to help us with this, and I talked about those earlier, from the microkernels to operating systems to the middleware. But designing these systems requires a lot of different skills. It's rarely something a single researcher can do on their own, because you've got to understand the computer engineering, computer science, the software, the systems design, all of which may have nothing to do with your actual HRI question, but you have to have all those together to build the system. And so generally, there's not much guidance out there to help us build these systems. There are some standards. There is little guidance, and what we need are some more standards definitions, in my mind, some performance models to help with how these systems should degrade as they're interacting, and some open source modular frameworks to give people kind of a bootstrap into the system, kind of a ROS for all the rest of the parts that isn't the ROS. And so this development complexity, and of course the lack of these resources, in our mind, inhibits some HRI prototyping and the research that go along with it.
Yeah, so building on Matt's list there, good answers to the following questions would really, really help, and one of those questions is, when are real-time systems actually required, right? When should we be prioritizing these things, and how can we fit that into like an asynchronous framework like ROS, right? And then sort of this general sort of question about like what infrastructure is actually appropriate, right? So we did it at 1,000 hertz because we could, but I mean, like that probably is overkill for a motion planning algorithm, But it's interesting to sort of think about like how we can actually, if we were to come up with like a modular framework, an open source modular framework, what would that infrastructure look like, for HRI? In addition, I think, we can actually take a lot of messages from other industries. So, my background was in avionics development, so that's the one I tend to go to. But in aviation, there's this like really formal procedure for developing and testing flight control systems. So what we would typically have is 3 stages. And you start off with your software and simulation, you have software in the loop, and then hardware in the loop, and then you get to like phased flight testing, right? As a very coordinated, practical way to validate your system design. And I think we can actually use a lot of that in HRI. And I think there's a lot of stuff that we can learn, right? So I think in general, like one thing I'm really interested in is the idea of developing like a relatively simple open source pipeline, for doing this kind of stuff. And particularly for compiling and deploying on dedicated computer infrastructures, right? So you can think almost like an image that you could, just use and build like a Docker container and then deploy, kind of similar to like an XPC type Matlab approach. But I think one of the things that, as a community, I think we should really be thinking about is, explicit guidance. Like when should we be using systems? How should they look? And then formal definitions that can inform us on what appropriate bandwidths, what bandwidths and latencies would be appropriate to maximize usability and responsiveness. So yeah, in conclusion, real-time HRI systems, just to tie it back to what we were talking about at the beginning, may become highly sought after in the coming years. And it's going to be tied to reshoring and labor shortages and an aging workforce, where these systems have a lot of tangible, practical usage in a manufacturing setting, and it's something that we can actually start thinking about now, right? And we can start doing a lot to make that path easier. So simple pipelines and rigorous definitions will go a long way. But it's also interesting to think about it from an academic standpoint, where, we could actually really start experimenting, with like real-time interactions if we actually develop these frameworks in a way that we can all collaborate and build them. So yeah, so I think that's pretty much it. Cool.
Great.